Kuanshi is a postdoctoral scholar based at Stanford University, works on the SimCenter project. This morning, he's going to be talking about building and using structural models from OpenSees in HydroUQ. So, Kuanshi, thanks for being here.
Thank you, Matt and AJ. And my pleasure to just share some of my experience and knowledge about this great tool, HydroUQ, and more from like a structural engineer perspective. And today, I think I just have a few topics want to share with you. I will first start with some review of the Tohoku earthquake and some building damage by tsunami, and starting from there, try to think about what we can do with current OpenSees and its basic modules in OpenSees and how they constructed in HydroUQ, and talking about introducing the user interface in the HydroUQ for running OpenSees, building structure model, running analysis with the event information from the CFD simulation, and then maybe share two examples. And these two examples just to want to demonstrate that the basic use and the workflow of this HydroUQ with OpenSees simulations. And okay, to start with the background, I saw a lot of the news actually back to 2011 when I was in college, and saw the video, terrifying video from YouTube and the television about how the tsunami swept through the east coast of Japan, and the magnitude of earthquake is 9.1, and estimated rupture is about 500 kilometers, and the estimated peak sleep is about 50 meters. Although the ruptures occur far away from the mainland of Japan, but then the tsunami height arriving at the east coast is already up to 20 to 30 feet, especially in the Iwate, Miyagi, and Fukushima, these three prefectures. And given this large amount of the water flowing through the east coast of the Japan, and this is actually a snapshot from Japanese building departments about after the disaster. They went back to the field and do the field assessments, and showing this human damage and the house damages and due to the tsunami. And looking into the table on the right, in the red box, you can see actually even we go into the complete deconstruction or missing, the total number of buildings, actually the amount of buildings huge, 70,000 buildings actually got completed damages. And then sharing some of the particular failure modes that observed in the site. So on the right is the one 3-story reinforced concrete building. It's kind of totally overturned by the wave action, and at the base level. And this could be due to the foundation issue, coupled with the inundation height is really high in this region, and the weaken the foundation, and then get it tipping, and then start to incline under the wave action. And another typical failure mode that saw a lot of plays are the story collapse mechanism. So in these two bottom figures, actually the building itself actually are two-story originally. And in this area, actually a very traditional construction type would be the first story with large opening for the for small stores or just for opening for public business. And for the second story, it's usually to be residential sections. And usually we'll have a much smaller window opening. So it's actually when the wave action going through the building, the second story actually bears a lot of wave forces, and then translated to the first story column, and the shear the column gets the story collapse mechanisms. And another interesting failure now at the global level, but locally at a specific facade of the wall of the building, here's on the right bottom figure, just showing one out of plan failure of a one reinforced concrete shear wall building for a storage building. And actually, as reported by the observer, they actually found some reinforcement fracture at the right bottom across the concrete cracking here. And so given all of this really terrifying pictures and maybe bad news from these old events, and try to make analysis and step back, think about like what we can do in terms of predicting those failures and assessing the structural damage due to the potential wave actions from big earthquakes and tsunamis. And so predicting the damage or loss for the building usually starting really with the field assessments. And this is usually done by trained staff and engineers went into the site and or rely on satellite images or information that for more regional level assessment. And then from that, develop empirical fragility and damage functions. For instance, in headers, develop the fragility function as showing the middle figure here, related to the damage ratio of a typical building with the occupancy type. Aside that damage ratio based on the peak water depths after a tsunami or hurricane. And more recently, I think that another strategy would be if we could do some more detailed structural modeling and then try to simulate the local responses of a typical wall or concrete column beam elements in the building, try to capture more detailed local failure modes as shown in the previous slide. And then based on the simulated responses and estimate those potential structural failure and the building collapse. And and basically in Hydro, I think the HydroUQ invokes OpenSees for analyzing building responses under the wave action, which from abstracted from the CFD simulation results. And the first of all, maybe I guess maybe for those who are not familiar with OpenSees, just to have a very quick few slides about briefly introduce OpenSees. So OpenSees is actually the short name for Open Systems for Earthquake Engineering Simulation, which is originally, of course, developed for as a software framework for parallel or sequential finite element applications earthquake engineering. But and it is originally written in primarily in the C++ with Tcl and the Python interpreter for user to build their own finite model. But it has recently been extended widely by different engineering communities for various applications, for instance, response simulations on the file and the soil structure interactions. And I want to mention that OpenSees is actually developed by our chief technical manager here, Dr. Frank McKenna. He has also developed the SimCenter general workflow, computational workflow for doing regional and individual simulations. And since OpenSees is sort of the backend application, it's actually called by many of other apps. So for instance, earthquake engineering app, HydroUQ analyzes the building responses under ground motion accelerations. And in VUQ analyzes the building responses to the wind pressure, and also now in the HydroUQ. And just want to quickly mention the main abstractions in the backend in the OpenSees itself. So OpenSees have 4 major components. First one is the model builder, where actually user can creating objects of the model, for instance, the node elements and the material constraints, boundary conditions, loads, and the time history of external loads to be applied on the building. And they have a domain to temporary state, store the current state of the model at the time t, and then the next step to advance. And then analysis module, solving the systems of equation of the model under the external load step by step, and then using the defined solution algorithm, integration methods, and convergence criteria, as well as other testing criteria. And the last component is a recorder. Basically, if you imagine that you are doing a waveform test or shake table test, you would like to attach a lot of sensors onto your building or the in the test setup. So just to record the responses of the of your interest. And similarly here in the virtual environment, once we build the numerical model, sort of recording, and it's actually user have more flexibility to record the different responses and measures from the simulation. And we will cover this a little bit later in this presentation. And so overall, this is four big abstractions in the OpenSees. So again, user starting with building the model and then define the analysis and then put recorders on the simulation and then launch a run to get to the simulation. And to mention, this is open source code. So if you, and the users can also be developers and to introduce new material types, new element types to advance their own simulation and also to facilitate others' research as well. And okay, so this four abstractions, except for the domain part, which is sitting in the back during the simulation, the other three actually have a good map or projection to our HydroUQ in the front end with its unique UI in user interface. So the model builder, which basically mapped to the SIM panel, structure information modeling, defining the model in parameters. And currently we have two options for HydroUQ. First one is the MDOF, which basically, as shown in the figure here, snapshot below, user can define how many stories and what's the story height and the story stiffness. And we will later have a simple example for this MDOF module. And second option would be for more advanced user, create their own OpenSees script in Tico and then upload their modeling script. And Hydro will automatically generate the model using the example, using the user-defined script. And the analysis abstraction is mapped to the FEM panel here to configure the analysis. And currently we also have two options. The first one is default analysis, specify the basic parameters from the UI, as you can see from the snapshot below here. Again, define the analysis type, integration, algorithm, convergence test, criteria, and the system of equation solver, and then the damping model for the building and the damping ratios and other options. And we will have like a quick example to walk through this different options later. And the second option for the FEM, again, is for more advanced user to upload their own defined algorithm to solve the numerical model that defined in the SIM panel. And the last abstraction is the recorder, which is actually mapped to our EDP panel here to define what engineering parameter demand to be monitored during the analysis. Similarly, two options. First is a very standard EDP type. So following quite a similar idea in the earthquake engineering, as a structural engineer, we are perhaps very interested in the peak story lateral displacement, peak story drift ratio, and peak acceleration at different story levels, and also the residual displacement for the building to assess the recovery stage of the building to help evaluate the recovery path. And the second option would be the user-defined, again, to upload a recorder script, and additionally provide the post-processing script for HydroUQ to read the recorder outputs and then feedback the results to the Hydro UI, so they can present, the UI can present and understand the results and calculating the statistics from the results. And we'll have a very detailed example and the example script to walk through to help you. And I think we can also share the recorder script and the post-processing script later after this training section. Yeah, just a quick recap. So 4 major abstraction in the OpenSees. model builder mapped to scene panel, domains holding back during the simulation analysis mapped to FEM to help define analysis setup. And the recorder is basically what we are interested in the structural responses from the simulation. And so now we have the building set up, and then we start to look the other side of the problem, the external load. And as AJ mentioned during the previous session, that we actually extracted the wave action from our CMD simulation. So here, just one example, HydroUQ simulation type from the wave Flume digital twin, and using the standard OSU flow. And imagine that we have a building model that's placed in the location as shown in the figure here, and with the defined building sizes. And imagine if this is sort of a scaled down model for a real building, then what would be the responses of the building under the wave action generated by the CFD simulation? I mean, like here, I would perhaps mention, emphasize that this simulation actually done without any coupling between the structure and also the fluid responses. It's more like a post-processing stage for CFD, and it generates the external loads for the building to do the separate analysis in the second stage. And so the forces from CFD, basically, we have obtained the pressure and viscous porous forces integrated from the pressure over the area of patch that we created for given the building geometry, story by story. So for each story, we actually calculate the horizontal and the vertical forces from the three components: pressure, viscous, and porous, and then map them to the building, apply them on the story nodes as defined in our model. And then you can imagine that the force here would be a time history applied on the story level. And then we start to analyze the building under the external loads. And just as a quick slide for the engineering demand parameters here, under the wave action, perhaps we are interested in reading the flow displacement as showing the two figures on the top that recorder at node 13 and the node 12. But then sometimes we are interested in the story drift ratio, which would be the differences of the story displacement from node 13 and node 12 and divided by the story height. So basically a very useful measure for structural engineer to map the story responses to potential story damage. And other responses as will be later see in the results, example results. Just want to mention here quickly, the FPFD, basically for the peak flow displacement, PID, peak inter-story drift ratio, PFA, peak flow acceleration, and the PRD is the peak roof drift ratio. And so now let's work through one basic example here, the MDOF module in the scene panel. So on the right figure here, I'm showing the user interface for the MDOF. So you could define the, just to pull out the laser points. Define the number of stories that you have. And then on the right, you will have images generated to indicate the model configuration. Define the flow weights for each node here and the story heights here, eventually for all the story. And individually, you can also modify the story height for specific story flow level here. And define the story stiffness and the yield strength. And inside the MDOF, we're actually calling this simple bilinear model for describing the story responses under cyclic external load. So the initial stiffness defined by the story stiffness X direction and the Y direction basically would be the tangent modules of this story display shear versus displacement curve. And the yield strength defines where the story starts to get first the yield point, and then have hardening stiffness describe the post yield behavior. And user can also specify really high yield strength here to generate a near elastic responses to make sure that the yield strength bigger enough. And here we also have the options for the mass eccentricity and the response eccentricity for defining the potential training or potential torsion responses that are due to irregular loads on the building. And to mention that this building as defined here in the first page in the MDOF actually has no information about what's the outside dimension and how they related to the simulated CFD results. So as I think AJ already worked through this page here about defining the building dimension here, specifically in the building table, type -2 means that this is the interested building that I want to record the responses. So, and then we define the building location of the center of the base, and then define the building parameters. And this building parameters, 3 numbers, basically indicates the depth along the wave direction, width of the building perpendicular to the wave direction, and the height of the building. Where these 3 numbers will be used to create a patch and calculate the projection area from the fluid pressure, and calculate the external story forces on the building in the back end. And again, okay, in this simple example, we are using the standard OSU Flume, and then as showing before, the building location here and the building size. And then for the boundary condition, I think that here we would like to define the inlet moving wall, and specifically to this plain text files for defining the moving wall displacement history, as well as the water depth history. So the first file here, the WM displacement new, basically the first digit here, first number here defines the time step, and then the following numbers defines the displacement history of the moving wall. And then the WM height text file would be to define the steady state water depth, and then the incremental change in the water depth history. And for the boundary condition, again, similar to the example AJ walks through, we define the exit and the top surface with the inlet outlet free, and then left, right, and bottom to mimic the boundary, like physics boundary condition using the wall with no slip. And in this example, we actually defined the flow weight and the story stiffness as a random variable. And so you try to understand what's the potential influence of different design parameters in structure, how they would influence the structural responses. And I think that summary and Kash covered part of this uncertainty quantification in yesterday's presentation. And hopefully we could review them back in the videos share later. But here, these 2 variables here, we define them as the normal distribution with the mean value and the standard deviation. And these 2, and with the generated sample, individuals simulation model were created with this realization drawn from the distribution defined here. And lastly, the final element application here. Want to walk through the these few options here. So the analysis, first is the analysis box, where we actually want to do a transit analysis type for the time integration through the external load history step by step. And we want to have 2 sub-levels with 10 sub-steps for each. And then for the integration method, here basically the integration schema just to define how the system of dynamic equilibrium equation would be solved for this transition problem. And the default algorithm is the numeric algorithm with alpha and a beta of 0.5 and 0.25 respectively. The user can change the alpha and the beta value here. And also other possible integration method would be central differential method, which is explicit method running with conditional stable time here to t. And the algorithm, the third option, a third box here would be the algorithm, basically to define a numerical algorithm solving the nonlinear equation, and which can be invoked by the nonlinear response behavior from the material or nonlinear geometry nonlinearities. And the default one is Newton-Raphson, and other available options including Newton-Raphson with initial stiffness, with the average stiffness. And then the convergence test, the fourth one, define how we commit analysis step. The default option is the norm unbalanced. Basically means that we try to try to track the unbalanced force in our analysis, and then with the tolerance 0.01 here and the 10 convergence step, and this 2 tolerance and the iteration steps can be defined by user. And the solver, the fifth box, defines the system's equation, how they will be stored in memory and solved. And the default one is the unsymmetric spar solver, UMF pack. And other variable solver would be the full generator, so basically full band and the symmetric band. And the damping model here define how we assign damping to the building. The default one is the Rayleigh damping, and you can define the damping ratio in this subdomain here, and select the tangent stiffness as the initial committed, and select where you pin the damping ratio to the mode, which mode you want to pin the damping ratio, and then once it's all set up with the MDOF theme and the event panel from CFD, and then the FEM algorithm, FEM analysis set up, and then the next step is just to submit the job. Here, maybe first log in on the right top button, and then click Run at Design Safe to submit the analysis. And then once the job submitted and acquainted, you start to click on the Get from Design Safe to retrieve the job status here. And then once you see the one job finished for its status, you could right click on specific job name and then click on the retrieve data to observe to get the result back. And then typically we'll finally arriving at this table once the results loaded correctly, and meaning the analysis finished without error. And again, from this tab, maybe I can just do side-by-side presentation now, because I want to demo how you could actually calculate the here. Perhaps I will load already pre-run examples, and the files I would be shared. The input files will be shared with you after the presentation. Yeah, and this typically will once the Dakota.json file be downloaded and loaded from the result from design safe. It will ask for a directory for your local, and that typically currently would be the same directory as your inputs. And as it's load back, you could start see the summary table first pumped out at the result panel, which on each row here describe one specific EDP, engineering demand parameter. For instance, here PFA means the peak flow acceleration. The first digits following is the story number, so the first story. And the second digit follow is the direction. One means in the X direction, two means in the Y direction, so the vertical direction. So in this case, we only have the wave flow in horizontal direction and with little peak acceleration in the vertical direction in the analysis, in the analyzed time history. And another tab here, aside the summary table, will be the data value, which is the previous page that I show in the result in the slide. And then you could start to plot the input parameters as a random variable we defined for the flow mass W, and then K, the story stiffness, and then also click through the column to get the response plot for each individual run. But then on each column, you can also click right to get the empirical CDF, and then to get the histogram. And also similar, I think the summary and Akash mentioned yesterday, you can also do some basic scatter plots to explore the general correlation. And based on this, you could back to the UQ panel to explore to do the sensitivity analysis to explore the relative importance of different design parameters as random variable here. And yeah, so this is the first simple example. Basically, we went through the MDOF system module in the SIM, and have another example here, second example for a bit more advanced version for defining a structural model. So instead of the MDOF, imagine that we have a building model to represent a four-story fictitious buildings here. And then instead of having the story-based stiffness and mass, we will have beam element and the column elements here. And typically, calling back that the example, we have the first story collapse mechanism. So we can actually record the base column force demand to our analysis and check that demand if exceeded its capacity to see if we can capture those failure modes in our analysis in the future. And so in this example, instead of going to the MDF panel module under the SIM, we actually go into the OpenSees building model generator option here. And for here, we will need to specify the path to the input script, and this can be done by click on the browser, click on the choose button here on the right, and then find out your main script for the OpenSees tickle. And I'll show this in the next slide, what the example script looks like. And then define the node response node, and those response nodes basically defines the column line where we want to apply our external force from the CFD simulation. And the last two boxes define the spatial dimension. Here we want to do only a simple 2D analysis with 3 DOFs for each node. And this is the example script that I uploaded in the previous page. So basically I have a few sections. I want to walk through them by very quickly. The first one is to define the random variable here. As mentioned, we want to define flow weight and the story stiffness as our random variable. And the command line here is to use the pset, and then followed by the variable name here. And the third number, the number following is just for initial number that will be pumped up in the user interface as the constant variable that you can change later in the user interface with different distribution types and mean and standard deviation values. And second section will be define some modeling parameters. Here we define the elastic modulus, the area of the column section, and the second moment of error for beam and column elements respectively, and also the G. And then the next section will be to define a model dimension as well as the DOF here. So again, here with this script just consistent with what we have in the user interface. The two boxes define our 2D model with 3 DOFs for each node. And then this fourth section is going to define the node, and the command line itself is starting with the node and then followed by the node tag, and then the X and the Z direction in the 2D model. And then with the mass optional arguments to define the mass in the 3 DOF respectively. So in this case, we only include the mass for X and the Z direction, so horizontal and vertical mass, ignoring the torsion, the rotational mass for the nodes here. And the fifth section here is define the boundary condition. So here I have the two base nodes indicating corresponding to the two column line here, node 1 and 6. And I try to define the fully fixed boundary condition. The command line itself is the fix and the node tag, and then the flag for the 3 degree of freedoms. 1 indicates fully fixed, 0 indicates free condition. And followed by a constraints section to define, because we want to limit the beam axial deformation for the beam element. So here what we can do is to constrain the two nodes for all nodes at the same story level to limit to force them to have same lateral displacement during analysis. This can be done by this equal DOF with the node tag 1, node tag 2, and the DOF direction to constrain their displacement. So here we use the first DOF, which is horizontal displacement. And then lastly will be 2 sections to define the column and the beam elements here. So the command line basically start with the elements and then define this elastic beam column elements, followed by the element tag here, first element connecting the first node and second node. This will be the first story column, and the second element connecting the node 2 and 3, third, which would be the second story left column, and then moving up to 4 story, and then for the other column line in the model, the elements from 5 to 8. And similarly, following the same elements command, define the beam elements. And limited over time, I cannot really dive into these details about all these command lines and also other possible valuable materials elements. Just want to mention the OpenSees has detailed online documentation, OpenSees wiki, for user to check and to explore possible material types, element types to use to model the building responses. And coupled with this user-defined structural model, user can also upload his or her analysis script. And here, let me see what. Okay, I think I only have 10 minutes. But, I will quickly walk through this example analysis script that can be used to replace the default setup. So first section here would be the gravity analysis, if any, and typically is following a similar schema, define the constraint systems equation type, test criteria, integration method. And for here, we use the load control for static analysis. and algorithm for solving nonlinear equations, Newton-Raphson as a default, static analysis type, and analyze one step of a gravity load. And after that, I want to wipe the analysis setup and start a new setup for the transient analysis under the external load wave action load history, and similarly define the system's type, integration method, test criteria, and algorithm, and following by another damping eigen analysis and damping section. And here I think that I forgot to mention that the eigen analysis by default is running into the AR pack, which is the Fortran 77 lab that to get the eigenvalue problem, eigenvalue from the system equation. And then other options would be from the lab pack will have the symmetric band option or the full band option. And again, want to mention this command line can be really have detailed documentations and documented online in the OpenSees wiki. But also please feel free to get us back if you have any questions or you want to explore more and getting a few examples to start with. Lastly, I want to cover the user-defined EDP. In the previous slides we covered, we have the default story-based EDP, but here, as mentioned, that for this four-story shear building model, we would like to record the base column shear. So here we define two response parameters, starting with v_1. This indicates that we will abstract the left column in the first story and its shear forces, and then the v2 means that we will extract the base shear for the right column in the first story. And the two additional inputs would be one recorder tickle and one post-processing tickle script. And these are the snapshots for the two tickle scripts. In the first recorder tickle, it's relatively simple. We want to record the envelope element responses for the first and second elements, basically the base columns, and write it into the element out, and just to record output the peak force responses here, local force. And the second script is the post-processing script. And here start with reading the element out, and then open a new results.out file where the results from the OpenSees element.out will be processed and written into this results out. And then this results out actually will be later processed by decoder and loaded by HydroUQ to generate the data table as we see in the UI. And for every defined EDP name, you can see I have a if clause here to decide whether it's the axial force or the shear, and give the right element tag to the extract the element tag from the EDP name, and then collect the element forces from the edit.out, and then output them into the results.out file. So these two scripts actually linked with each other and called by the decoder in the backend to generate and to read and understand the output format and the data the user want to collect and present in the user interface. And I think that I'm sort of running to the last few minutes. Maybe have some questions, but the last example would be the detailed building model, where instead of the MDOF and the shear building model, we will have really detailed response simulations for a steel moment frame here. And for each story for each beam and a column. Instead of defining elastic elements, we start to introduce nonlinear response here. And for instance, this is just one type of the hinge, nonlinear hinge to describe the beam and the column response under cyclic external load, including the strength deterioration and stiffness deterioration to explicitly simulate those potential failure modes in our analysis. And I think with this said, I will just close my presentation today with this recap slide. And I'm happy to answer questions. And thank you for your attention and time.